And we are back. So last time we looked at examples of plane stress, but now we want to look at examples where the stress state may be more complex and we may have three-dimensional stress. So if we want a general rotation matrix, we could use this rotation matrix called Q, which takes the cosine of the angle between when we have a 3D stress state. So we have coordinate system or axes 1, 2, and 3. A is going to be the angle between 1, 1 prime, B, 1, and 2 prime, C, 1, 3 prime, etc., 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 etc. So we can calculate this Q matrix or Q transformation matrix, and we can find our new stress state here using this transformation matrix here. So this is a valuable tool, a valuable and very general equation that we could use. Note we have to do the transpose, dot with our original stress matrix, and then get over here. So that's the key thing. So let's go ahead and let's try to find these angles and write a robust code that will allow us to do this, because I don't want to calculate this each time. So I've got my original basis set here. So my one axis is just my vector 1, 0, 0, two axis 0, 1, 0, again, in your coordinate system. I can build a rotation matrix where, let's say I want to rotate around my 3 axis. So I just want to rotate basically the 1, 2 plane. So I could build rotation matrix using Mathematica here, and I could set an angle. So for example, if I want to try to recover, the same answers we got over here, because we were looking at a 3D stress state, but we were just rotating the 1, 2 plane, that minus 15 degrees, we can go ahead and do a rotation matrix for 15 degrees here, or minus 15, whatever you want to do. Actually, we can do minus 15. So I can do my rotation matrix here, minus 15, minus 15, minus 15. I'm going to rotate here. So these would give us, once I do this rotation matrix and I'm applying it towards this vector, it will rotate. So it makes sense, right? This rotation matrix should rotate my one axis by that amount. But look at the last value. I'm rotating around the one axis, so the 3 axis, excuse me. So this shouldn't change. But when I'm rotating the 1, 2 plane, my 1 prime will be different from my 1, my 2 prime will be different from my 2, but my 3 prime and my 3 are exactly the same. So now I could look at and develop, basically look at the angle between my original basis set. So basically, if we look at the code here, I'm looking at my first value here, so my first angle, or my first basis 1, and then I'm looking at the angle between my original 1 vector, or my 1 axis, my 1, 0, 0, and what's the angle between the new 1 prime, 2 prime, 3 prime. So I'm basically filling out this Q rotation matrix here. So I've got my original basis set, new basis set, and I can find that Q. So stress 1. We can also use these transformation matrix are very general. So like this is a transformation if I have that 1/6 around the 1 axis for stress and strain. And the same thing for around the 2 axis. And then this one would be around the 3 axis as well. So I could go ahead and use that and compare my answers again. So write it in the Voigt notation, like we saw previously. If I rotate, let's do minus 15. Here's my theta here. So I could write the values here. I could do my transpose here, and then I could get those values here. So you can see I'm getting the same results, actually this is for, let's do minus 15. Oops. Let's move it over here. So I'm getting the same results here. So you can see 12.3, 7.6, 5.961. 12.3, 7.6, 5.961. We're getting the same values effectively here. And we could look at this and compare that all the way up here, 12.3, 7.6, 5.9. It's the same answers. It's beautiful. This is the nice part about working with, solid mechanics. So this is really kind of the beauty of these problems. Now, next time we're going to get into eigenvectors and eigenvalues and how we could kind of show those rotations again. So I'll see you all in the next video. Thanks. Bye.